Alrighty, well, this video is on Chapter 3 of the textbook, and it deals with the topic of moments. The first thing you need to understand is that a lot of times, while engineering and physics are very similar subjects, uh, engineers will have a different vocabulary, a different set of terms that they use different from physicists. And the moment is especially one of these terms. So for physics, we have this thing called torque. And torque, of course, was like the rotational version of a force. If you're given, let's say, a stick, and you apply a force to this stick in a certain way, it can make the stick, of course, rotate, turn, spin, however you want to say it. And what we found in physics was that the torque, which is the Greek letter tau, was given by R cross F, where all of these are vectors. R is the distance from the point of rotation to the point of application of the force. F, of course, is the force we're talking about. And the big thing here is that the product, the operation, is a cross product. And cross product is a very fancy operation, and it comes up because we're dealing with vectors. What we found in calculus, of course, multivariable calculus, but we also talked about it in physics, is that once you start dealing with vectors, all of a sudden the rules of mathematics are different. So we know we can add and subtract, multiply and divide numbers. Those are all scalars. We know the rules of adding numbers together. It's easy. It's commutative, associative, all these different things. But we also found that when we dealt with vectors, we still have something called addition, but that operation is different than for scalars. It's not so easy to add vectors together. And in fact, what we found was the rule said you can only add vectors together if they happen to be in the same direction. And if they're not in the same direction, then we had ways of getting around it. We, break everything up into components, add the components together separately, and then you can combine everything together using the Pythagorean theorem and all of that. And so the rules of mathematics for vectors are different, and we know the rules for addition. We've done it plenty of times. Well, of course, same thing is true in multiplication. It turns out that when you deal with vectors, there's not just one type of multiplication, but three. Now, certainly at the beginning of the semester, one of the mathematical review things we did dealt specifically with cross products when we talked about solving systems of equations, and I said there's a fancy way of solving these equations, which is called Cramer's rule, and we use matrices and everything to do it. The determinant of the matrix, you divide the x1 over the Vronsky and whatnot. Well, it turns out we're going to be doing a similar thing when we try to calculate what's called a cross product. Before we get into that, what you need to understand about what a cross product is as a form of multiplication is, at the end of the day, what you're doing is you're taking things which are perpendicular to each other and getting a new vector which is also perpendicular. So anytime you see a cross product between vectors, you have to think perpendicular. If we think about in physics, when we talked about torque, the important thing was the force had to be perpendicular to the distance. For instance, if I had a wrench, here's a bolt, here's my wrench handle. If I push straight down, with a force. Here's the bolt, so that's the point of rotation. The distance is from here to where the force is being applied, so this is vertical distance, and the force is a vertical force. Well, obviously, if you look at that, pushing down on a wrench like this will not cause the wrench to rotate. In fact, pushing this way will make the wrench rotate. And so anywhere in between, you're going to have some angle here. Some component of that force will make it rotate. And of course, we can see quite clearly the x component of this force will go into rotation. The y component won't do anything. It's just pushing straight down, doesn't try to make the thing rotate. So when we talk about torque, we're always talking about the force is perpendicular to the distance, or the distance is perpendicular to the force, depending on which way is easier to think about. So anytime you talk about torque, you're always thinking these things have to be perpendicular to each other. Well, what's nice about the cross product is even if at first the force and the distance are not purely perpendicular, the act of doing a cross product will inevitably only create the perpendicular stuff for you. So it's good in that you can take the vectors as they are without modifying them, do whatever the operation tells you to do, and it only takes into account the perpendicular stuff. So that's very nice. And that's why we use the cross product to calculate this torque. Of course, the cross product operation is a little bit more complicated than sometimes, just find the perpendicular component of the force and just multiply by the distance. They both give you the same thing, but depending on what question you're working on, this version of doing things, of finding the component and multiplying, might be easier, or this version might be easier because it's too complicated. Maybe you have 15 different forces and you don't feel like having to find a perpendicular component for every single force. So you just do the cross product and be done with it. So that's the first thing you need to know. Next, second, of course, is the fact that what we in physics call torque, engineers call moment. So the torque is the same as a moment. They mean exactly the same thing. It's just a different word. So instead of using tau as r cross f, the engineers say moment m is r cross f. Okay, so capital M stands for moment. Moment and torque are the same. Well, the best way to get into moments is, of course, an example. Let's take exactly this example of a wrench. Here's a bolt, here's a wrench. I apply a force of 100 newtons at an angle of 30 degrees with respect to the horizontal. If we let the wrench handle be 0.5 meters, the question is find the moment caused by the force. All right, so if I were a physicist, what I would say is, okay, in order for this force to rotate the object, I only need how much of my force is perpendicular. So I would first take the force, here's the force, make a right triangle, this is 100, this is 30 degrees, x component, y component, and I look at my problem and I say, well, the distance here is a vertical distance, and so the force which will cause rotation is a horizontal force, so I only want the x component. So I say the force x component is going to be 100 cosine 30, which is 86.6. And then I say the moment is r cross f. What's the distance? 0.5 meters. What's the force which causes the rotation? That is, what's the perpendicular force? 86.6. And of course we get 43.3 And the units are Newton meters. So pretty easy. The key, of course, is you want to only calculate or only use in your calculation the perpendicular components. And so sometimes it's beneficial to take all the forces in your problem, break all of them up into x and y components, and then use the x and y components as necessary, whichever ones are necessary for your particular situation. In this case, because the distance from point of rotation to where the force is hitting is calculated vertically, then I only want a horizontal component of the force. If, of course, the distance is calculated horizontally, then I only want a vertical component. Now the question is, what happens when the distance or the force or both are neither horizontal or vertical, but are at angles? You know, let's say our wrench is not straight up into the air, but is kind of leaning over. Well, now we still need to get the perpendicular component, but now the perpendicular component doesn't mean x or y, it's some other thing. How do we handle something like this? That's what my next example is going to talk about. In order to do it, I first want to introduce a bit of notation that you might not have seen before, but is kind of standard, and it's definitely standard in mathematics, and it's definitely standard in engineering too. And in physics, we do it. Unfortunately, what you're going to find is we all have different notation. Generally speaking, mathematics and physics, we're so related. We use very, very similar, if not exactly the same notation. And that is this. Given a vector v, we can write the vector in what's called IJK format. And it looks something like this. Let's say it's 2i hat minus 3j hat plus 4k hat. Okay? This means something very specific. This is a vector, and what it says is 2 units in the x direction. Okay? So I hat is a symbol which means x direction. Now, obviously, they could have called it x hat. That would have made sense. But generally speaking, when you're working with equations, the variables in your equations are probably x, y, and z, and things like this. And so mathematicians were afraid that there could be a lot of confusion with the x as a variable in your equation and x hat as a direction. So instead of worrying about it, they just said, well, we just won't use x hat, we'll call it I hat. So IJK stands for XYZ. So J hat, of course, Y direction. And K hat, Z direction. And so you could have a vector V, which is I hat plus 2j hat. And what this would mean is the x component is 1, the y component is 2, and the z component is 0. And that's what we mean by 2 units in the x direction. That's the same as saying the x component of my vector is 2. So you could see already, if you're kind of thinking about it, this is a very beneficial notation. As opposed to something like this, where you have, some vector v is 20 meters per second at an angle of 30 degrees. Well, we already know, based on all the physics we've taken, that the first thing we have to do is break this up into components. So you have to say, okay, what's the Vx component, what's the Vy component, what's the Vz, and then you do whatever it is you need to do for your problem. So the first step is take this vector and break it into components. But here, you look at this vector, it's already broken into components. So I could just use the components. I don't have to do sines and cosines or anything like that. It's sitting there for me, ready to use. So I say there's different notations. What you will have to be ready for if you go into an engineering program is they will make even bit more shorthand than this because engineers are lazy. And they'll say this is the same as 2 minus 3, comma 4. Okay? And it's just up to you to understand that what they mean is 2, the x component is 2, the y component is minus 3, the z component is 4. They just don't write it as an equation, and they don't write it with the I hat, j hat, k hat specifically. They just give you this kind of coordinate system, and you have to know, because you're an engineer, oh, this means the same thing as this other thing. It's just a faster way of writing it. Now, likely, I'm a physicist, I'm not an engineer, although my PhD is an engineering PhD. I'm going to use I, J, and K because it's what I'm used to. But if you look in engineering textbooks, or if you take a class in an engineering school, just be ready that a lot of times they'll use this notation instead of IJK the way I'm going to use it. They mean exactly the same thing. So with that said, let's do an example where we have to make use of this. Here's an example. Say you have a rod. Okay, and the rod is like this. And it's hinged to the floor. Okay. So obviously, because it's hinged, it's free to rotate about the hinge. It could rotate down, almost like windshield wipers or something like that. And what we know is that this rod makes an angle of 65 degrees with respect to the ground. And then there's a force that will be applied to the rod in this direction. Some force. Let's say that force is 20 degrees, and this force, makes an angle with respect to the horizontal of, let's say, 25 degrees. Okay? Given the rod has a length from here to here, the length of this rod, let's say, is 9 inches. So I'm about to do a problem that's in not the English system. Yeah, the English system of units. So that is what we use in America, inches and pounds instead of meters and newtons. Everything is the same. It's just the units you're gonna be, foot pounds and things like that. Don't worry about the units. It's just I don't want you to think it's 9 meters long. Okay. So we have a force applied to this rod. The rod is allowed to rotate. We know that the length of the rod is 9, and the rod's sitting there at an angle currently, and we know the angles. And of course the question is find the moment of the force about point A, where point A, let's say, is the hinge. Okay? Well, now we have a problem which is similar to what I said previously, which is now it's not so easy to figure out what is the perpendicular component because the rod is not already either in the x or the y direction. If the rod were sticking straight up, that's a y direction, then obviously I just take the force, I only want the x component of the force, and now I'm perpendicular. But here the rod is at an angle. So I have two options. I can either try to figure out what would be the perpendicular component of my force to the rod, which is at this weird angle. It won't be X or Y, it's going to be some other weird thing. Or I can make use of the vector version of this equation, which is what I'll show here. The vector version. So the vector version says this. We're going to say moment is R cross F, and we're actually going to do the cross product with the vectors. Well, in order to do it, the first thing we need is what is the R vector and what is the F vector. Because in order to do a cross product, I need to know what these vectors are. So how do I figure out what these vectors are? Well, let's look at the system. Let's look at R first. In order to find R vector, what that means is, I'll redraw this little picture here so it's clean. Here's my rod. I want a vector that starts here and points to here. Okay, so this vector, so this is point A. This is where the force is. So I want, if this were to be like a little coordinate system, X, Y, and Z, I want a vector that tells me where, an equation that tells me where this vector is pointing. Well, we can do that. And what it means is, what's the X, Y, and Z component of that arrow I drew? Well, let's find out. First thing, I can make a little triangle. Here's the Y component. Here's the X component. And the Z component, that's this three-dimensional in and out thing. We're going to pretend like this is straight on. So the Z component's just going to be 0. It's not coming out towards us. It's not going away from us. It's purely in the plane as if I drew it on the chalkboard. Okay, so X component here, Y component here. What do I know? What I know is this is the angle 65. So, well, we've done this. We found components before. The X component of R. Well, first of all, the hypotenuse is 9, so it's 9 cosine 65. But my vector's pointing to the left, so he must be negative. So I get out my calculator, I say 9 cosine 65, and I get negative 3.8. The Y component, similarly, I look at my triangle. The Y side is the side opposite to the angle. So that means I use sine. So it's going to be 9 sine 65. He's pointing upwards, so he's positive. So I get 8.16. So there we go. And then, of course, we know the Z, because I said specifically it's not pointing out towards us or anything. That's just 0. All right, good. Now, what do? I write down my little equation for my R vector. It's the X component, negative 3.8 I hat. And then the Y component, plus 8.16 J hat. And then I could just call it plus 0 K hat. Okay? So now I know what the vector representation of my R, the distance, is. 3.8 to the left, 8.16 up. Well, now I need to do the same thing for my F. Well, let's look at the F. Here's F here. What do I know? Make my little triangle. There's the X side, there's the Y side. Y, X, I know this angle here is 25. And of course I know that the force itself is 20. So, what's Fx? Well, let me, there's not enough room here. Fx, well, let's look. X component, that's the side adjacent, so that's cosine, so 20 cosine 25. He is pointing to the right, so he's positive. So I get out my calculator, I say 20 times the cosine of 25, and I get 18.13. And I do the same for y. The y component, 20 sine 25. My force is pointing downwards, so I have to make it negative. So he's negative. And I get negative 8.45. And of course the z, again, I'm not coming out or away or anything, that's just 0. All right. So now I have all the force stuff, so I make my little vector notation. The x component, that's 18.13 I hat. Negative 8.45 j hat. And 0 k hat. So that was a lot of the hard work done. I had to take the information in my problem and create vectors out of them. Of course, I know how to do that from all the stuff I've been doing in physics before, which is finding components. So I get the x and y and z component of every single vector, and I make my little vector notations for the things I need, the r vector and the f vector. Now that that's done, I've only got one thing left to do, and that is to use those vectors to calculate my moment. So now I use my equation. M is r cross f. How do I do r cross f? Well, this is something you learn in mathematics first, usually. If you haven't seen it in mathematics, then you're going to learn it from me. You're going to make a matrix. The matrix is going to have 3 rows and 3 columns. So it's a 3 by 3 matrix. The first row are your directions. So we have I hat, that's the x direction, j hat, the y direction, and k hat. Okay, so there's the first row done. It's just the directions. The second row is whatever this first vector is. For us, it's r. So we say, okay, we have negative 3.8 is the first, 8.16 is the second, and 0 is the third. And obviously, you can tell the third row is going to be whatever the second vector is, f. So, 18.13, negative 8.45, and 0. So now we've created a matrix basically out of 3 different vectors. The first vector, the first row, are your directions, x, y, and z. In our case, we call them I, j, and k. The second row is whatever the first vector is in the cross product. So for us, it's r cross f, so r goes first. It's the second row. So you put the little x, or the I hat, j hat, k hat coefficients into the second row, and then of course the last row is whatever the last vector is. R cross f, f is the last vector, so we have the components of f. Now, to finish it off, to actually solve the cross product, we take the determinant of this matrix. Now, like I said, if you don't remember how to do determinants, go back to the Cramer's rule video I posted for if you have systems of equations and you want to solve them in a fancy way. I showed you how to use Cramer's rule, and part of Cramer's rule was you set up a matrix and you take its determinant. And then with Cramer's rule, you do more stuff after that. You divide and stuff. Here we just have to do the determinant and that's it. So let's do it. How do we do a determinant? Well, if you remember, you start with the first element, which is I hat. And then you pretend to strike out the row that I is in and the column that I is in. So I would do this. I would say, okay, we're on I, so we take out his row and his column. And so obviously all that's left is this little 2 by 2 square here. Okay, so being that, with that little 2 by 2 square, what do? You take the little cross product. This is why it's called a cross product. You do 8.16 times the bottom right 0, and then you subtract the other way. So it's like cross, multiply, and subtract. So what do we have? 8.16 times 0 minus negative 8.45 times his 0. I did that in gray by accident, but that's fine. And so now I'm done with the I piece. I now move to the second one. I'm now on J. And remember the big rule where a lot of people forget this, you subtract the J. And now what do? Well, just like before, you take J's row and J's column away. And you can see we only have these terms here. So we're going to do the little cross, multiply, and subtract for them. So we say negative 3.8 times the bottom right 0 minus 18.13 times the top right 0. And now the J piece is done. So we move on to K. K is the last one, so we do plus K hat. And again, we do the same thing. Get rid of K's row and K's column. And of course, what's left is this little 2 by 2 piece here. So we do the cross multiply and subtract for him. So we say 8.16 times 0. I'm sorry, what am I doing? Not that at all. Negative 3.8 times negative 8.45 minus 18.13 times 8.16. And now we're good. Now all we have to do is actually get our calculator and do all of these multiplying and subtracting and stuff. So what do we get? Well, notice the I piece. This times 0, that's 0. This times 0, that's 0. So this whole term goes to 0. No I piece in it. What about the J? 3.8 times 0, he's 0, and this is also 0. So the whole J piece goes to 0 too. What about K? Oh, there's no zeros here, so we're going to have to do the math. Okay, well, we've got negative 3.8 times negative 8.45. That gives me 32.11. And then the other piece minus is 18.13 times 8.16 is 147.94. And all of that is multiplying K hat. So now we just subtract these, 32.11 minus that stuff there. And we get negative 115.8 K hat. That's the answer. What does the answer mean? What's the physical interpretation here? Because I'm being told I want the moment, which is like the torque, and first of all, I'm given a negative answer. Well, that's okay. That just means the direction is the opposite direction. No big deal. But I have a direction here. That means the torque points in a certain direction. Well, this is kind of a formality. In physics and engineering, when we define a torque or a moment, we have to give it some direction. And the reason we give it a direction is so we understand, are we talking about a clockwise rotation or a counterclockwise rotation? Because if I tell you, oh yeah, I'm going to rotate this bar using a torque of 5, well, okay, am I making a bar rotate clockwise or am I rotating counterclockwise? That may make a difference to me. If I'm building an engine and I want my tires to make my car go forward, Well, I better know if my tires are going to spin clockwise or counterclockwise, because if they're going in opposite directions, I'm not going to go forward at all. And so the rule is this. It's called the right-hand rule. And it says, I'll do it on another page so I don't mess that up. If we're looking at the top, okay, so let's say this is a wheel. Then, if the wheel rotates counterclockwise, like this, imagine putting your fingers, let's say you put your hand down on a piece of paper, or let's say you put it on the computer screen if you're watching this on a computer screen, so that your thumb is pointing directly at you, and the edge of your hand is on the screen, and you wrap your fingers in this counterclockwise direction. If you put your hand on there, and remember, this is your right hand because it's called the right-hand rule. If you do that, notice how your thumb is pointing either up from the paper or directly out of the screen. That's called the positive k-hat direction, or the positive z direction. Because when we deal with coordinate systems, if this is x pointing to the right, y pointing up, those are my positives. X, Y, Z is positive pointing outwards towards you. So we define when our right hand, or the fingers of our right hand, spin counterclockwise, my thumb points in the positive Z direction. That's called a positive moment, or positive torque. So if you look here, we got negative 115 k-hat. What that's telling me is the moment points into the paper or into the screen. That means if you point your thumb into the screen and see how your fingers wrap, they're now wrapping clockwise instead of counterclockwise. Well, should that be true? Look at the picture. If you remember what we're doing, we had this rod sitting here and the force is applied in this weird direction. Which way will the rod rotate? Well, obviously to me, the rod's going to rotate like that, clockwise. That's exactly what we found here with this negative k-hat direction. That just means it's clockwise rotation. So if you want to know the physical interpretation of this directionality, the negative sign and all of that, it's just telling you, is it clockwise or counterclockwise? But anyway, this is a second way to solve moment problems. Now, this is a little tedious, especially this part here where we had to find the vector notation of our two vectors, our r vector and our f vector. But actually doing this part, the actual cross product, is really not that bad. And what you're going to find with a lot of our problems, unless they're three-dimensional, a lot of the terms drop to zero. You get a lot of zeros in this matrix. Not always. We're going to have some problems that don't have any zeros in it. But the cross product, as long as you play by the rules and you do everything appropriately, that's pretty easy. That's kind of like you stick your quarter in the machine and you just crank the machine and you get out the answer. This piece over here, the vector version, the vector notation stuff, is setting everything up. Taking the vectors that are in your problem, writing out the vector notation form. Once you have that form, now you can do your cross product. The other version is what we did over here, physics. In this case, finding the perpendicular component was quite easy. So we didn't have to go through the trouble of all the vector notation stuff. We could skip all of it and do the easy version, which is calculate the perpendicular component of the force and multiply that number times the distance. What we do in this case and what we do in this case are the same thing, believe it or not. It's just for this case, because not everything is set up nice and straightforward where you could get the perpendicular component easy, trying to do that other version is actually quite difficult. But I could find X and Y stuff quite easy. Finding x and y stuff gave me all of these components over here. That I can do in my sleep. I've done it so often. So I use this version of solving the problem when I don't know how to get perpendicular components. When I do know how to get perpendicular components, I use this version. That's my own way of doing things. I'm not forcing you to follow that. If you want to use the cross product version for every problem, you go ahead and do it. You can do it for this problem. All you have to do is say, okay, well, let's try it. Again, I want R and I want F. So what's the R vector? Well, if you remember for this problem, we had a rod sticking up from the ground. Here's the point of rotation. Here's where the force is happening. I'm told from here to here is 0.5 meters. Say, okay, well, what's the R vector? What I'm looking for is a vector that points from the origin to this point here. So there's my vector. So I want the x, y, and z component of this vector. Look at the vector. What's the x piece? 0. He's not pointing in the x direction. So 0 I hat. What about the y direction? He's pointing straight up, and the length of this vector is 0.5. So it's plus 0.5 j hat. And how much is pointing out of the page or into the page? 0, of course, in this case. So there's the R vector notation. What about F? Well, F points down like this. 100, and we have this 30-degree angle. So what's the x piece? X is cosine, so it's 100 cosine 30 is the I piece. The j piece is minus, because it's pointing downward, 100 sine 30. And the k piece is going to be 0 again. So 86.6 I hat minus 50 j hat plus 0 k hat. All right, so now I have my R and my F. I want to find the moment. So I do the cross product of I, j, k. R is 0, 0.50. F is 86.6, negative 50, 0. And now I go through the process, and I'm just doing this quickly because I've already shown you how to do this. You can go back and fill in the steps to show that I'm doing it right, but just to show you we should get the same answer or something very, very close within rounding error. So I start with I, and I have 0.5 times 0 minus negative 50 times 0 minus j, 0 times 0 minus 86.6 times 0 plus k, 0 times negative 50 minus 86.6 times 0.5. So that's all 0. That's all 0. This is 0. So I get minus 0.5 times 86.6 is 43.3 k hat. And what do you know? Same answer. So they both worked, and they both work every time. So I'm not trying to tell you you should use this version for these problems, but if you have this other problem, you have to use this other way of doing things. That's not true. These are just a bunch of tools. And while certain tools are better for certain problems, that doesn't mean that's the only tool you're allowed to use. Here's a problem. I had 2 different ways of solving it. To me, this way was a lot faster. And so that's why I chose to do it that way the first time. However, it might be that you're so good at doing cross products that you like doing this way better. It certainly looks like it may take a little more time and it takes more writing, but that doesn't mean it's wrong. Go ahead and use that way. So you have 2 ways of attacking these types of problems. The old physics way, which works sometimes, if the problems are set up nice and neat. When they're not, or you're unsure, this is the more general way of doing it, because that is the actual technique. This way that I call the physicsy way of doing it is a shortcut. When we teach general physics, we're purposely giving you problems that are easier so that you learn kind of the thought process and the system without being burdened by having really complicated situations. When you go further into physics, you're going to have harder problems, and all of a sudden that's when we start using this more general form of the actual cross product itself. And now you're seeing an example of it here in an engineering course. But they both work. And so what you're going to find with the practice problems that I post and their solutions is sometimes I may have two versions, two ways of solving it. Or I may solve it different than the way you solved it. What matters is at the end of the day, when we get our answers, do we match? Now I'm going to warn you, depending on how much you round versus how much I round, the answers may not come out perfect. And I'll give you an example. This problem I did here, this is actually, I believe I did this problem on the practice problems. And there's a solution to it on there. I don't think the answer was negative 115.8. I think it was more like negative 116.3 or something like that. Slightly different. So don't be afraid if when you get an answer, you're off by 1 or 2 or something. That may just be that either you rounded kind of up here when you got these numbers, and maybe I didn't, or I had more decimal points, more decimal positions. And so all that rounding stuff affected the answer by the time we got to the end of the day. Or vice versa, maybe you kept more positions and I rounded. So if you got 116 and I got 115, that doesn't mean you're wrong. It's just slight rounding mistakes. And I'm going to take this into account when I'm grading, and it makes it harder on me. But the way I can do it is I'm going to pay major attention to your work. I'm going to see, what do these look like? Do they look similar to what I have, or are they very far off? And then when you do this process, are you doing the steps correctly? Did you remember this negative in front of the J? Are you remember these negatives here? If you have everything right, but your answer was off by 1 or 2, well, you're still getting 100 for the question because you did it right. It's just we rounded differently, and that's okay. I do want you to be very careful, however. I'm the teacher now. If you go off to engineering school, you'll have other professors. Some professors are way more strict. I'm not doing anything about significant digits. I'm not even mentioning it in my class because, to me, I would rather you not worry about significant figures and only worry about the material. And then later, as you get good and you're sure you want this to be your profession, then you can worry about significant figures because it's not clouding your judgment on how to learn this material anymore. It's just a detail. But technically speaking, if we're going to do everything correctly as if you're working for an engineering firm, then we should always get exactly the same answers because we will always round the same, because we will follow certain rules. And those rules are called significant figures. And it deals with, well, if you add or subtract, then you keep a certain number of decimal points. If you multiply and divide, you keep a different number. And it all depends on how the numbers are given to you. I'm not dealing with any of it. If you follow those rules, that's really good, because then you won't have to worry in the future. If you're not following the rules, neither am I, because you could just look at my work. Sometimes I have 1 decimal place, sometimes I have 2. Why the heck do I do that? I don't know. I'm lazy. And I'm not getting my work checked by an engineering firm. If I were getting paid to get these answers, I'd be doing everything precisely. And I wouldn't be rounding, as if it doesn't matter. Anyway, all that is to say, as you start practicing these problems that are posted, when you check your solutions versus my solutions and we're just slightly off, don't think you're necessarily doing anything wrong. It's probably just a rounding thing. Now, if you're off by 100, or if it's significantly off, then yeah, there's a problem and you need to look for it. But like I said, if I'm 120 and you're 121 or 119.2, that's fine. It's just a rounding thing. Anyway, this is moments. This is probably the biggest topic you're going to have for this course. Almost everything we're about to do when we deal with bridges and structures and things like that, you need to have moments down pat. And so I have a lot of practice problems posted, some pretty complicated questions and some not so complicated. I'm telling you right now, you have to be responsible and force yourself to sit down and work these problems. I've been lax this semester with, how much homework to give you and stuff like that. Mostly because you're adults and I don't think I need to baby you. But I'm just giving you a word of advice, especially for when we have a test. You have to be able to do this. And this is usually where a lot of people have questions, especially at the beginning. Should I use negative or positive? Why is the distance this number instead of this other number? When do I use a perpendicular component or blah, blah, blah? The only way to get it down is to practice them. I will be giving another video where I work a few more problems out. So I'll try to give you some more examples to hear me and watch me solve them. But you also have my solutions with the practice problems posted. I will be given a homework assignment on this because I think it's important enough to make sure you're working some. But also be responsible for yourself and know to take this particular topic seriously, because everything we do from here on out requires your ability to do this 100%. And it's kind of like when you first start into physics and I talk about vectors and how important components are for vectors, because generally that's the very first piece you do before you even worry about equations. Well, here in statics, you have to be able to do moments, because in general, that'll be the first equation you use before you move on to the rest of the problem. So you have to be very, very good and very, very fast with calculating moments. They're very easy, and a lot of them will be done like this right here, the easy version. But for the very complicated problems, you're going to have stuff like this to do. Okay? Get good at it. And then when we have these other problems where we're dealing with bridges and stuff, you're going to be satisfied because we're using these easy versions. But you know deep down that you can do a more complicated version if you had to. All right, so I hope this was informative. If you have questions about it as you're working these problems, please email me. That's what I'm here for, to help guide you with things you're not understanding. But you need to work these problems big time. So until next time.